Hello everyone! In this lecture, we will explore the browser extension mechanism and the related ecosystem. As you probably know, extensions are like apps for our browser, and according to statistics, the majority of users have installed at least one extension to customize their browsing experience. Essentially, extensions can be used to add new features to the browser, modify web content, and automate tasks. Let's begin by looking at how extension installation and usage appears from the end user's perspective. Let's use the excellent Privacy Badger extension as an example. This is a useful extension as it blocks known trackers and can be enabled to discover unknown trackers by analyzing the behavior of third-party scripts loaded by websites. Note that in this lecture we will focus mainly on Chrome extensions, as Chromium-based browsers cover nearly 80% of the user base. Firefox and Safari have similar extension systems and use a technology that is compatible with Chrome's, so it is actually possible to create a cross-browser extension that works on all major browsers. Now, to install an extension, we need to find it on the Chrome Web Store. By default, users are only able to install extensions from within the Chrome Web Store. It is possible to bypass this restriction by going to the browser's extension page and enabling developer mode. Then it is possible to load unpacked extensions from the file system. Anyhow, after we click Add to Chrome, a permission prompt will pop up. So it says that the extension can read and change all data on all websites and change privacy-related settings. So at this point, the user must assess whether the extension is trustworthy enough to be granted such access. As you will see, the permission to read and change all data on all websites is extremely powerful with a very high potential for abuse. Unfortunately, most extensions will require this powerful permission, as without it, they cannot fully customize the user's browsing experience. So here, the user must simply trust that the extension will not abuse this capability. After we click on Add Extension, the extension will be installed. Once installed, the extension can be pinned to the toolbar and when clicked can show this type of pop-up, which underneath is just a website that is shipped within the extension. The extension can also contain standalone web pages. For example, if we click on the options here, the extension's option page will open, which can be used to configure the extension. Note the special Chrome extension scheme here and the unique ID of the extension. Basically, that's how extensions look from the end user's perspective. Let's look at how extensions appear from the developer's perspective. Under the hood, there isn't really anything particularly complicated. It is possible to create a simple extension in just a couple of minutes. A typical extension consists of HTML, JavaScript, and CSS files bundled together using a zip archive. Here you can see a directory structure of an unpacked extension. Let's go over the most important components. Every extension requires a JSON formatted file named manifest.json, which specifies important information about the extension's components and permissions. Then, a service worker is a JavaScript file that runs in the background and has access to powerful browser APIs that are provided exclusively to browser extensions. So, the service worker can access browser data and observe the browser's activities. The service worker, however, cannot access the DOM of the open website. There is a content script that is injected in web pages and can therefore access and modify the DOM and, if necessary, can communicate with the service worker. So, these two are the most important components of an extension. Then, if necessary, an extension can include pop-up and HTML pages, which can be used to provide a UI for interacting with the user. And finally, icons in different resolutions for the extensions button. Let's take a closer look at how this works by inspecting a simple test extension. The content of the manifest file is quite straightforward. First, we define the manifest version 3, which is the latest version of the extension platform. Then the name and version of our extension. For permissions, we request storage and web navigation permissions. The storage permission allows our extensions to store and retrieve data from a persistent storage area, and the web navigation permission lets us monitor and interact with the navigation events of web pages. Then we specify our service worker script and content scripts. For content scripts, we can specify on which pages the content script should be injected. This here matches example.com and all its subdomains. And finally, we specified that this page should be displayed when the user clicks on our extension icon. And in our case, the content of this page displays hello from extension. A service worker is a script that runs in the background independently of the lifetime of a web page and doesn't require any user interaction. The service worker has no direct access to the page's DOM. However, it has access to the web extension's APIs, which provide almost full control over the browser. For instance, it can intercept HTTP requests, access most of the data stored inside the browser, and react to events such as navigating to a new page, removing a bookmark, or closing a tab. Which of the APIs the extension can use depends on the respective permissions declared in the manifest file. Note that a service worker performs event-driven processing, meaning that it listens for events associated with browser activity and then reacts to them. Service workers are terminated when idle and restarted when an event they are listening for is triggered. Let's look at an example service worker used by our extension. Here, it listens for the web navigation on completed event and receives the details object when it is triggered. Note that in Chromium, the web extension's APIs are located under the Chrome namespace. Once a navigation event is received, we log the URL to which the user navigated. We also store the last URL in the browser storage. The storage API can be used to store data in a way that persists across sessions and is accessible from different parts of the extension. For instance, it can be accessed by the service worker, content scripts, pop-up pages, and also other pages of the extension. We can inspect the storage data under the application menu in DevTools. And finally, our service worker performs a POST request submitting the captured tab ID and URL to a remote server. So effectively, this extension links every website we visit to a remote server. Not nice from a privacy perspective. What makes matters worse is that detecting such filtration can be quite difficult. Since the service worker operates in the background, the requests it makes will not appear in the website's network logs. To monitor the network activity of a service worker, we would have to open the browser's extension page and click here on the service worker link. This will launch a detached developer tools window where we can inspect network requests made by the service and the data log to console. Of course, a malicious extension will likely send out collected data once per day rather than on every page visit, making it even more difficult to detect. Alternatively, we could audit the extension's JavaScript files, but that may be far from trivial, especially for large and complicated code base. Anyhow, so that's about service workers. A content script is a script that is injected in the web pages specified in the manifest file. By default, the content script runs after the page has been loaded. For instance, this script will replace the entire content of a web page with the text hello from extension. So it has full access to the DOM, and effectively, an extension can use a content script to achieve the cross-site scripting capability in a website where it is injected. The dangers of such a capability should now be very obvious to you. Now, while content scripts can use standard DOM APIs to read and modify web pages, the resulting changes made to the web page will be restricted by the website's content security policy. However, an extension can bypass this by modifying the HTTP response headers. For instance, here is code from a service worker that removes the content security policy header and also the X-frame options header. This is a very dangerous thing for an extension to do, as it effectively makes all websites in the user's browser vulnerable to script injection and clickjacking attacks. Also, because the content script runs in the security context of the particular website, it can abuse the permissions granted to the website. For example, if a user has granted geolocation access to the website, a malicious content script can detect this and obtain the user's geolocation. The same applies to any other permissions granted to the website. I hope that this is obvious to you. Now, contrary to a service worker, a content script has access to only a limited set of web extensions APIs. This limitation is in place to reduce the impact in case a malicious website exploits a flaw to execute arbitrary code in the website's browser process. If necessary, the extension can bypass this limitation by having the content script request the service worker to perform a privileged action. The content script can use various methods for communication with the service worker, such as the storage API, or by using the sendMessage method to send arbitrary data objects. The service worker would need to add an event listener to listen for messages and perform the requested action when the message is received, possibly returning the result. To summarize, the content script has full control over a web page and can communicate with other components of the extension. Let's take a quick look at what permissions an extension can request. Here is a list of the permissions that will be displayed among the permissions that the extension requests. Then there are also permissions considered basic capabilities and therefore will not be listed among the permissions granted to the extension. However, these still need to be defined in the manifest file for the extension to access the respective APIs. Now, this scary read and change all your data on all websites warning will be shown when an extension requests any of these permissions, and also when the extension's content script is injected into web pages, as this also provides such a dangerous capability for the extension. The problem is that most extensions will require this capability, and in fact there are only few very specialized extensions in the Chrome Web Store that do not trigger this scary warning. It is also difficult for users to determine whether an extension has valid reasons to request such extensive privileges. As a result, users are often forced to accept such permission requests without much consideration. Google's policies forbid extensions from requesting permissions that are not necessary for the main functionality of the extension. However, in practice, it is common for malicious extensions to request excessive permissions under false pretenses, making it appear like these extensions are actually required. Usually, this is justified by the extension implementing some useless feature that requires the particular excessive permission. The goal of the attacker is to later update the extension with a malicious version that will abuse these permissions. The attackers want to avoid requesting new permissions in extension updates because in such cases, Chrome's extension updater will disable the extension until the user manually re-enables it by consenting to the requested permissions. We will discuss malicious extensions in more detail, but first let's take a look at the Chrome Web Store and its role in the extension ecosystem. The Chrome Web Store serves as the official marketplace for Chrome extensions. Today, it hosts around 150,000 extensions. However, the majority of them are outdated, with almost 60% of extensions having last been updated more than 2 years ago. Google is supposed to maintain law and order within the Web Store, but the reality is that Google doesn't have it under control. While the policies that publishers and extensions must comply with are strict, there is almost a complete lack of policy enforcement. There are ways to report non-compliant extensions, but in practice policy violations are largely ignored. Researchers complain that even reports of malicious extensions go unanswered. Malicious extensions are typically removed only after issues are brought to light in media publications. Fake reviews and ratings are another major problem. It is common to see overly positive reviews by users that miss the actual functionality of the extension and simply express the excitement about how the extension changed their lives. Such fake reviews can be purchased for as little as $1 each, and Google states that it does not verify the authenticity of reviews and ratings. Then, inflated user counts are also common. Since the user count contributes to the search ranking, the number of extension users is often artificially inflated by bots. Another way to influence search rankings is through keyword spamming. For instance, when searching for Privacy Badger, several unrelated extensions appear in the results. These extensions mention Privacy Badger in their descriptions, which is picked up by the search engine. And since this search is performed across different languages, some extensions add a list of keywords to the translations of their descriptions in less popular languages. Then, the featured badge is meant to provide assurance about the quality of the extension. The Privacy Badger extension has the feature badge, and it states that the extension follows recommended practices for Chrome extensions. In practice, however, this is a weak security indicator as it is relatively easy to obtain it. In fact, authors of malicious extensions often put extra effort into obtaining this badge, as it also affects the ranking of the extension. The established publisher badge is more meaningful, as it helps identify the entity behind the extension. For the Privacy Badger extension, it states that it has been created by the owner of the listed website, and since we know that the website is owned by a reputable organization defending digital privacy, we can reasonably trust that the published extension is not malicious. And also, using extensions developed by Google should be the preferred choice. The point is that we should always conduct a background check before installing random extensions. If the author is just a random person without a GitHub and social media presence, that should raise a red flag. Now, one significant conceptual issue with the Chrome Web Store is the lack of monetization features that would allow developers to charge money for extensions. As a result, there is a strong incentives for extension developers to collect and sell user data or to sell the entire extension to fraudsters once it has built a substantial user base. Developers of popular extensions are often spammed with offers to sell their extensions. The amount offered depends on the user base, and it can be very tempting for the developer to sell an extension that otherwise provides no financial return. Once the extension is sold and transferred, the new owner can push updates, which will be automatically accepted and installed by the browsers of existing users. So, the transfer of an extension's ownership is a very strong indicator that the extension will turn malicious. Unfortunately, Chrome does not notify users of ownership changes. And to avoid raising alarms, some fraudsters even purchase the entire developer's Google account, making the ownership change invisible to the public. But alright, isn't Google supposed to check extensions and updates before they are published in the Chrome Web Store? Google claims that every extension undergoes a rigorous examination, but in practice, only some automated sanity checks are applied. So, Google uses automated tools that rely on heuristics to detect problematic behavior in extensions such as malware patterns. Of course, this type of automated analysis can be bypassed, allowing to ship malicious code or code that violates policies. Manual code reviews would help here, but code audits can be problematic, first due to obfuscated code. While code obfuscation is prohibited by the Web Store policies, minification is still allowed, and some forms of obfuscation can be achieved by simply developing the code in a very convoluted way. A bigger problem, however, is remotely hosted code, where the extension executes code downloaded from a remote server. This renders code auditing pretty meaningless, as the behavior of the extension depends on the code provided by the remote server. For instance, an extension can use this type of code to fetch a remote script and inject it into the current web page. Malicious extensions exploit this functionality to hide their harmful behavior. Initially, a seemingly harmless script is served, but over time it may evolve to include malicious functionality. The code may change at any time, and to avoid detection, may target users in specific geographic regions or users who have been using the extension for a while. The use of remotely hosted code is often justified as a means to simplify maintenance, allowing the functionality to be updated without frequently updating the extension itself. Now, the latest Manifest version 3 prohibits remotely hosted code, meaning that all code must be contained within the extension itself. This is enforced technically by removing the ability to execute script here and by enforcing a content security policy on the extension's content scripts. The problem, however, is that the Web Store policy still allows remote configuration, meaning that configuration data can be fetched from a remote server. Malicious extensions exploit this to bypass the restriction on remotely hosted code. Dynamic object method invocation is one such technique employed. The thing is that JavaScript supports bracket notation for dynamically invoking object methods. So this allows us to specify in brackets a string variable that stores the method name. And similarly, bracket notation can be used to access properties of an object. So an extension can abuse this feature by fetching these parameters from a remote server. The result is that by looking at this type of code, we cannot tell what exactly it does with the web page, unless we know what is stored in these configuration variables that are fetched from a remote server. Some extensions go even as far as shipping an embedded JavaScript interpreter within the extension. Here is an example of using such an interpreter to call the console.log method. Let's take a deeper look at various types of malicious extensions. Malicious extensions are prevalent in the Chrome Web Store. This is especially common among ad blockers. Most of the ad blockers in the Chrome Web Store are either outright malicious or waiting to accumulate users before turning malicious. Some of these ad blockers are forked versions of open source products, while others have been built from scratch and are barely functional. Yet, based on the reviews, a large number of users have installed them. One of the most common attacks executed by malicious browser extensions is the user's browsing history collection, meaning the extension tracks the pages the user visits and sends them to a third-party service. This is what is usually collected about each page visit. Basically, each address the user navigates to, along with a unique randomly generated user identifier that is sent in all requests. Top advertisers are very interested in obtaining such high-quality browsing data. Therefore, they often reach out to the developers of popular extensions, offering a simple way to generate additional income by collecting anonymous browser behavior data while following all privacy regulations, and personal information of users is not of interest at all. Now, the claim that such data is anonymous is a lie, as it is fairly easy to de-anonymize such browsing histories, especially for users who frequently visit their social media profiles. The Chrome Web Store policies prohibit collecting private information that is not necessary for the purpose of the extension, so this would be a violation of these policies. Nevertheless, the notorious Avast browser extension collected each visited URL under the pretext that the collection was necessary to improve the functionality of their product, while in reality, the collected data was sold to advertisers. The result was that Avast was fined by FTC and also by the Czech Data Protection Authority for violations of the GDPR. So, browsing history collection is something that is done even by extensions which are otherwise harmless and fulfill their main functionality. Then, affiliate fraud is another type of attack where the attacker collects a commission offered by online shopping affiliate programs. For example, when a user visits Booking.com, the extension sets their affiliate cookie, so when the user makes a purchase, the extension's owner is paid a commission by Booking.com for referring the user to Booking.com, while actually the extension did nothing to contribute to the user making the purchase. A huge scam was recently exposed when it was discovered that the Honey extension owned by PayPal performs such affiliate fraud. The extension claims to apply the cheapest discount coupon available, while in reality it injects their own affiliate cookie, collecting the vast majority of the commission for itself. Then, ad injection is when an extension adds advertisements to the websites a user visits. Similarly to affiliate fraud, the goal is to monetize the impressions and earn money from clicks. While this is prohibited by the Chrome Web Store policies, detecting such ad injection may not be trivial unless the user can distinguish legitimate ads from the injected ones. Then, search hijacking is when an extension redirects the user to alternative search engines when the user enters the search term. This allows attackers to artificially inflate search engine traffic, profiting from ad impressions and clicks. Such search hijacking is not stealthy and is likely to result in negative reviews by frustrated users. Lastly, password stealing is probably the worst thing a malicious extension can do. Most often, this occurs when attackers compromise the web store accounts of legitimate extensions. For instance, this code from the backdoor mega extension steals credentials for several services such as GitHub and Google, and then exfiltrates them to an external website. In this case, the backdoor code was quickly detected when the malicious extension update requested new permissions to read data on all websites. This raised suspicions among some users, and the code was discovered by inspecting the extension's source code. The discovery was published in the media, and the extension was removed from the Chrome Web Store. Now, when an extension is removed from the Chrome Web Store, it remains in users' browsers and continues to function unless Google marks it as malicious. So the outcome depends on how Google classifies the removal. There may be malicious extensions removed from Google for policy violations, in which case they will continue to harm users who have already installed them. So what are the measures that we can apply to stay safe in the extension ecosystem? Well, the first measure is to avoid installing an extension if the same task can be accomplished in another way. For instance, there are online tools that can be used to convert a document to PDF, so there may be no need to install a browser extension for that. Then, doing a background check on the entity behind the extension can help. Is there a reputable person or company behind the extension? Is the extension open source, developed transparently with development spanning several years? And things like that. And as a last resort, Chrome provides an option to enable the extension's website access only upon click. So it is possible to select this extension can read and change site data when you click the extension. Then, when the extension's icon is clicked, Chrome will offer to reload the page with the extension having access to the website. So this will restrict the websites on which the content script is injected, but will not help much if the extension's service worker has been granted permissions that allow it to read data from all websites using other means. But alright, that concludes the lecture. Thank you for watching.